Right now, inside a nitrogen-filled vault at the Johnson Space Center in Houston, there are pieces of the moon that no human being has ever touched with bare skin. Right now, not in 1969, today. A researcher in a cleanroom suit is reaching toward a sealed container that has not been opened since the day it left the lunar surface. And what comes out of it could rewrite a page of space history that most people think closed more than 50 years ago. Because here's the part almost nobody tells you when they talk about Apollo 11. The mission didn't end when Neil Armstrong and Buzz Aldrin splashed back down in the Pacific Ocean. It just went quiet. And in that quiet, for 5 decades, scientists have been arguing, retracting, and re-arguing about what those first moon rocks actually proved. Some of that argument only got resolved this year. We all know the postcard version. July the 20th, 1969. 1. Small step. A flag, some footprints, a plaque that says, "We came in peace for all mankind." That's the story that gets replayed every anniversary, and it's true, but it's incomplete. The way a photograph is true, but incomplete. The photograph doesn't show what happened after the cameras stopped rolling. It doesn't show the boxes of lunar soil and rock that got flown back to Texas under armed guard. It doesn't show the scientists who spent the next half-century finding out that some of what those samples seemed to say about the moon was, in places, simply wrong, and that only very recently has anyone figured out why. Here is the scene as it's happening right now. Apollo 11 launched from Kennedy Space Center on July 16, 1969. 4 days later, on July the 20th, the lunar module Eagle touched down on the Sea of Tranquility. Armstrong and Aldrin were on the surface for roughly 2.5 hours, moving fast, working a checklist under conditions no engineer on Earth could fully simulate. In that window, they gathered about 22 kilograms of rock, soil, and dust. 22 kilograms. 22 kilograms, call it 48.5 pounds, or about the weight of a large travel suitcase. Scooped, chipped, and vacuum-packed by 2 men in bulky suits, moving in 1/6 gravity, racing a clock because their oxygen and their mission, timeline, were both finite. That handful of suitcase-weight material is, today, one of the most studied groups of objects in the history of science. Not one of the most studied rocks. One of the most studied objects, period, rivaling anything ever pulled out of an ocean trench or a particle collider. Before any of that material reached a lab bench, it went through something the postcard version of this story almost never mentions: quarantine. NASA didn't know in 1969 whether the moon might carry something dangerous, some unknown lunar microbe capable of harming Earth's biosphere. So Armstrong, Aldrin, and Michael Collins spent weeks isolated after splashdown, and the rocks themselves were handled behind sealed barriers at the newly built Lunar Receiving Laboratory in Houston, treated, quite literally, like they might be carrying something alive. Nothing was. But the fact that an entire national space agency planned for that possibility tells you something about how much genuine uncertainty surrounded this mission. Uncertainty that rarely survives the cleaned-up highlight reel. And they didn't just grab rocks. Before they left, Aldrin deployed a small set of instruments called the Early Apollo Scientific Experiments Package. One of those instruments was a seismometer, the first seismometer ever placed on a world other than Earth. It was built to listen. It sat there on the dust, silently, after the astronauts flew home, doing something almost nobody was talking about at the ticker tape parades, recording the moon's pulse. For about 3 weeks, 21 days in total. This device shivered awake every time the ground beneath it moved. It caught faint signals. It caught vibrations so small that the instrument could detect an astronaut shifting in his sleep back when the crew was still on site. 3 weeks. Just 3 weeks. That's all the time this first lunar seismometer had before Houston lost contact with it, likely from overheating in the unfiltered lunar sun. But in that short window, it planted a question that scientists are still chasing today. What exactly is going on inside the moon? This is where the hidden truth starts to show its edges. Not some grand cover-up, nothing that dramatic, just the ordinary, undertold reality of how science actually works. Apollo 11 didn't hand humanity a finished answer about the moon. It handed humanity a stack of open questions wrapped in 22 kilograms of rock and 21 days of tremors, and researchers have spent the decades since then trying to read what's written inside. Some of the loudest disagreements in lunar science about magnetism, about the moon's interior, about whether the data even meant what the first generation of scientists thought it meant, didn't get settled in the Apollo era. Some of them didn't get settled until this decade. One of them, as we'll get into, wasn't resolved until February of 2026. So if the popular version of Apollo 11 is a hero's journey with a clean ending, flag planted, mission accomplished, cue the credits, the real version is messier and, honestly, more interesting. It's a decades-long slow-burn investigation, still active, still producing headlines, still occasionally overturning what we thought we understood. Samples collected in 1969 are, right now, sitting in vaults that NASA has deliberately never opened. on the theory that future instruments that didn't exist when Armstrong was alive, would be able to ask those rocks questions nobody in 1969 knew how to ask. Which raises the obvious question, the one that pulls us into the next part of this story. If scientists have had these rocks in hand for more than 50 years, why are some of the biggest mysteries about them only being solved now? What exactly did Apollo 11 find that took half a century to understand? And what's still locked away, untouched, waiting? That's where we go next. Into the numbers, the vaults, and the parts of the Apollo 11 story that don't usually make the anniversary broadcast. Think about that vault in Houston for a second. It's climate controlled. It's purged with nitrogen to keep out moisture and ordinary Earth air. It's guarded, not against thieves, but against contamination, against the risk that decades of exposure to our atmosphere, our humidity, our bacteria could quietly corrupt a scientific record older than complex life on this planet. That's not paranoia. That's precision. And it's the kind of detail that never makes the anniversary broadcast. Because NASA carefully manages humidity, doesn't sell as well as one small step for man. But it's exactly why we can still ask new questions of 50-year-old rock. It's why this story isn't finished. Let's talk numbers, because the numbers are where this story stops sounding like a legend and starts sounding like a case file. 22 kilograms of lunar material came home on Apollo 11. 22 kilograms. To put that in perspective, that's less material than most people check in a single piece of airline luggage. And yet, it produced more peer-reviewed research than entire subfields of Earth geology. Zoom out, and Apollo 11's haul turns out to be just the opening chapter. Across all 6 crewed landings between 1969 and 1972, Apollo astronauts eventually brought home 382 kilograms of lunar rock, core samples, and dust, to 196 individual specimens in total, which means Apollo 11's 22 kilograms, the sample that started it all, is less than 6% of everything NASA has ever collected from the moon. A down payment on the entire field of lunar science, not the final word. One single sample from that haul, cataloged as sample 184, a scoop of fine lunar soils, has on its own generated hundreds of scientific papers, hundreds from one scoop of dust. Bruce Jolliffe, a planetary geologist at Washington University in St. Louis, has called sample 184 one of the most studied geological samples that exists anywhere, and he's one of the researchers who's contributed more than a few of those papers himself. Now stack that against the seismometer. 21 days. 21 days of listening before the Apollo 11 instrument fell silent, likely. Overwhelmed by heat it wasn't shielded against. In those 21 days, it picked up dozens of unexplained signals. Slow building, slow fading vibrations. Researchers labeled L events, detected 83 times, an average of about 4 every single day the instrument was awake. It was so sensitive it picked up the astronauts moving in their sleep before they left the surface. Imagine an instrument sensitive enough to hear someone roll over in bed, deployed on a world 384,000 kilometers away, running on solar panels for 3 weeks before going dark. And in that entire recording window, 63 combined days once you add in the follow-up instrument from Apollo 12, researchers found not one signal that matched the pattern of an ordinary Earth-style earthquake. Not one. The moon, it turned out, doesn't shake the way Earth does. It groans deep and slow from moonquakes generally happening somewhere between 700 and 1,000 kilometers down. Deeper than almost any earthquake ever recorded on our own planet. Here's the number that should stop. 4.5 billion years. That's the age of the moon itself. An analysis of the Apollo 11 rocks helps cement a theory that sounds almost too violent to be true. That the moon isn't some captured asteroid or a separate world that wandered close to Earth, but a chunk of the young Earth itself blasted into orbit after a Mars-sized object slammed into our planet in its earliest infancy. The chemistry backs it up. Isotope ratios in Apollo samples line up so closely with Earth rock that the two bodies look, chemically, less like neighbors and more like siblings. That single insight, drawn straight out of Apollo 11's 22 kilograms, reshaped the giant impact hypothesis from a fringe idea into the leading explanation for why we have a moon at all. But here's the mystery that took the longest to crack, and it's the one worth sitting with. For decades, some Apollo rocks came back magnetized, not faintly. Some samples showed magnetic signatures strong enough to rival Earth's own magnetic field on a world that, today, has no global magnetic field whatsoever. None. Zero. A dead magnetic world, producing rocks that acted like they'd been forged inside a dynamo as powerful as our planet's core. For 50 years, that didn't make sense. The moon is small. It cooled fast. By most models, it simply shouldn't have had the internal heat to drive a long-lasting magnetic dynamo the way Earth does. And yet, There the readings were, sample after sample, refusing to cooperate with the models. That contradiction sat unresolved from the Apollo era all the way into 2026. 57 years of scientists publishing competing papers, some arguing for a long-lived lunar magnetic field lasting over 1 billion years, others insisting the readings had to be some kind of artifact or contamination. Both camps had data. Neither could fully explain the other side's numbers. It's the kind of scientific stalemate that never gets its own headline because researchers still disagree, doesn't trend. But it sat there, unresolved, for half a century, hiding in plain sight inside rocks sitting in labeled boxes in Houston. Then, in February of 2026, a team led by Claire Nichols at the University of Oxford published a study in the journal Nature Geoscience that finally reconciled both sides. Their answer: the moon's magnetic field was mostly weak, almost non-existent, for nearly all of its 4.5 billion year history, but every so often, for shockingly brief windows, it spiked, not gently. Nichols and her team found evidence of bursts of magnetism that could briefly exceed the strength of Earth's own field today, triggered by the melting of rare, titanium-rich material near the boundary between the moon's core and mantle. And by brief, we mean brief. For very short periods of time, no more than 5,000 years, Nichols explained, describing windows that in some cases may have lasted only a few decades. A few decades out of 4.5 billion years. The Apollo astronauts, without knowing it, had happened to grab rocks from exactly those rare, short-lived, high titanium hotspots, which is why their samples looked like proof of a powerful, long-lived magnetic moon that, for the vast majority of its history, simply wasn't there. 57 years to resolve a paradox, hiding inside 22 kilograms of rock most people assumed, had already told science everything it had to say. None of this happened by accident, and none of it happened without cost. Behind every one of those numbers is a person or a small team of people who bet years of their working life on the idea that this was worth doing. Start with the astronauts, because it's easy to forget how narrow their margin for error actually was. Armstrong and Aldrin had roughly 2.5 hours on the surface. 2.5 hours. In that window, they had to collect a contingency sample immediately in case they had to abort early, deploy the science package, take photographs, and gather that full 22 kilograms, all while managing suits that were essentially personal spacecraft, all while their heart rates and oxygen consumption were being monitored in real time back in Houston. There was no reshoot. There was no second landing that week if something went wrong. Whatever they brought home was what science would have to work with, possibly for years. Then there are the scientists who were waiting for them. Ghislaine Crozaz, who went on to study Apollo samples for decades, described watching the landing in July 1969 the way most of the world did, glued to a screen, stunned. In her words, she and her colleagues watched with awe, like billions of other people on Earth. But unlike most of those billions, Crozaz then had to go to work. She and a team were stationed at the Lunar Receiving Laboratory in Houston, waiting through a mandatory quarantine period before they were finally allocated their first samples at the start of September, roughly 6 weeks after splashdown. 6 weeks of waiting, after a lifetime of waiting for the space age to arrive at all. Once the material came through, teams worked around the clock to prepare findings for the very first Apollo 11 Lunar Science Conference, the event that would eventually become today's Lunar and Planetary Science Conference, still running, still the central gathering point for this entire field more than 50 years later. There's a kind of dedication in this story that borders on stubbornness, the good kind. Ryan Ziegler, who now curates NASA's Apollo sample collection, has talked about arriving as a graduate student in 1998 and being genuinely surprised that scientists were still poring over 30-year-old moon rocks. He's since spent much of his career being one of those scientists. And that's the pattern across this entire field. People who assumed the story was finished, discovering it wasn't, and then dedicating years, sometimes entire careers, to squeezing new answers out of old material. The engineers who built the instruments deserve their own credit here too. The passive seismic experiment that Aldrin deployed was designed under enormous constraints. Power budget, weight budget, heat tolerance, all of it. Dictated by the brutal math of what a rocket could actually lift to the moon and back. It ran on 2 small solar panel arrays. It had no active cooling beyond a basic thermal design, which is very likely why it went dark after just 3 weeks, cooked by lunar daytime heat with nowhere for that heat to escape. Engineers took that lesson and rebuilt the instrument with an added heat shield for the follow-up missions, and those improved seismometers on Apollo the 12, 14, 15, and 16 kept transmitting all the way until 1977, 8 years of near-continuous data from a redesign born directly out of Apollo 11's 3-week failure. That's the unglamorous, unsung version of scientific progress, Not a triumphant breakthrough, but an engineering team quietly fixing what broke and doubling down. That philosophy has a name inside NASA now, the Apollo Next Generation Sample Analysis Program, or ANGSA. Its entire mission is to take those untouched containers, some sealed since the exact afternoon they were collected, and finally open them, decades later, with instruments built for exactly this moment. In 2019, 50 years almost to the day after Apollo 11, an ANGSA team unsealed a vacuum-packed sample from Apollo 17 that had never been opened at all. Jessica Barnes, a scientist at the University of Arizona who worked on that sample, described the moment plainly: opening. It, she said, felt like a whole new lunar sample return mission. Lori Glaze, who at the time led NASA's Planetary Science Division, put the entire strategy into a single sentence: return samples are an investment in the future. And Jamie Elsala, an astrochemist at NASA's Goddard Space Flight Center, has described the underlying idea even more directly: that the whole point of bringing material home is to let scientists not yet born use instruments, not yet developed, to finally answer the questions Apollo-era researchers didn't even know to ask yet. There's real risk braided through all of this too, and it isn't just historical. NASA has, for decades, deliberately kept a portion of the Apollo sample collection completely untouched. Vacuum sealed, frozen, or preserved under helium, some of it never opened, even once since it was collected on the lunar surface. That's a bet. It's a bet that future instruments, future techniques, future scientists not yet born in 1969 would be able to ask better questions of that material than anyone alive at the time could ask. Researchers at Argonne National Laboratory, working with the University of Chicago's Center for Advanced Radiation Sources, have specifically praised NASA for that foresight. As one project member on that team has put it, the space agency understood that there would be new ways to study them, decades down the line, new ways that didn't exist yet, using tools like X-ray and neutron imaging that let researchers see inside rock samples without cutting or destroying them. And this isn't just an academic curiosity. The stakes reach forward. The same questions Apollo 11 raised about the moon's interior, its magnetic history, and its geologic makeup are directly relevant to where humans are trying to go next, including the lunar South Pole, where future missions hope to find usable water ice. Understanding whether the moon ever had a real protective magnetic field changes how scientists think about radiation exposure, about the preservation of ice deposits, about resource potential for future crews. A 57-year-old scientific argument about magnetized rocks isn't just trivia. It's groundwork for whether the next generation of astronauts can safely build something that lasts on the moon's surface. That's the part of the Apollo 11 story that rarely gets told at anniversary galas. It isn't a single triumphant afternoon in 1969. It's a relay race, handed down from astronauts to lab scientists, to graduate students, to engineers, to the researchers. Publishing new papers in 2026, each one adding a piece the last person couldn't see, which brings up the obvious next question. If it took 57 years just to explain the magnetism in these rocks, what else is still sitting in that Houston vault sealed, waiting for the right tool and the right mind to come along? So what happens now? What's actually still ahead of us? Not speculation, but scheduled, funded, in-progress work. Start with the samples themselves. NASA's Lunar Sample Laboratory in Houston still holds material from Apollo 11 and the 5 later landing missions that has never been unsealed, some of it vacuum-packed or frozen the moment it left the lunar surface in the late 1960s and early 1970s. That material is being opened in stages, deliberately, using facilities like Argonne's Advanced Photon Source and Oak Ridge National Laboratory's neutron imaging instruments, tools that can look inside a rock without slicing it apart, tools that simply didn't exist when Armstrong and Aldrin picked that rock up. Researchers at Oak Ridge have specifically used neutron imaging to search for hydrogen signatures inside these samples because neutrons make hydrogen visually pop out in ways other methods can't, hunting for water-related chemistry hidden inside grains that were assumed for decades to be bone dry. Every year, more of that sealed material gets its first real look, and every look carries the chance of overturning something else we thought we understood. And it isn't only the magnetism story that's been rewritten recently. Scientists studying zircon crystals, a mineral that acts almost like a tiny geological clock, pulled from the Apollo collection, have used high-precision dating to identify a major, previously unrecognized melting event on the moon dated to roughly 4,338 billion years ago. Lead researcher Melanie Barboni of Arizona State University described finding a strange gap of almost 100 million years with essentially no new zircon formation, followed by a sudden concentrated burst of crystallization. A pattern, she said, pointed to a single catastrophic impact large enough to briefly remelt part of the moon's already solid crust. That result was published only last year. Grains of mineral, smaller than a grain of sand, sitting in Apollo sample drawers for half a century, just quietly rewrote a chapter of the moon's early violent history. Then there's the return to the moon itself, and here the timeline has been anything but settled. NASA's Artemis program has already flown 2 missions, Artemis the Firm in November 2022, an uncrewed test flight, and Artemis II, a crewed flight around the moon, which launched April 1st, 2026, carrying astronauts Reed Wiseman, Victor Glover, and Christina Koch, along with Canadian astronaut Jeremy Hansen. That mission tested the Orion spacecraft and its systems on a free return trajectory past the moon before splashing down safely back on Earth. Artemis III, originally billed as the mission that would put astronauts back on the lunar surface for the first time since Apollo 17 in 1972, has been restructured. As of this year, it's now planned as an Earth orbit test flight, currently targeted for late 2027, designed to rehearse rendezvous and docking between Orion and the commercial landers being built by SpaceX and Blue Origin. The actual crewed lunar landing has shifted to Artemis IV, targeted for early 2028, with a second landing attempt, Artemis V, penciled in for later that same year. NASA Administrator Jared Isaacman has been candid about the uncertainty, telling a congressional hearing this spring that the timeline for that Earth orbit test alone could land anywhere from mid to late 2027, an admission that, even with modern engineering and 50 extra years of experience since Apollo, putting boots back on the moon is still fundamentally hard. That uncertainty is worth sitting with for a second because it echoes something true about the entire Apollo 11 story. Even now, with more computing power and a single Artemis mission control terminal than existed on the entire planet in 1969, the schedule still slips, the engineering still surprises people, and nature still doesn't care about our press releases. And the open questions keep stacking up. If the moon's magnetic field really did spike into brief, powerful bursts driven by melting titanium-rich material near its core mantle boundary, are there other, undiscovered pockets of that same chemistry elsewhere in the moon's interior? And would they still be capable of doing it again, even briefly? Nichols and her Oxford colleagues have suggested their next step is testing more of the Apollo collection specifically for that pattern, a weak background hum interrupted by rare colossal spikes, to see how often it really happened and where. That work is ongoing right now, using rocks that came home in 1969. There's also the matter of what other space agencies are finding. China's Chang'e 6 mission returned the first ever samples from the far side of the moon, adding a second, previously unavailable dataset to compare against everything Apollo brought back from the near side and early. Analysis of those far side samples has already started reshaping questions about why the moon's 2 hemispheres look so different from each other. Every new sample from every new mission becomes another cross-check against the Apollo baseline, another chance to confirm or quietly overturn something scientists thought they understood since 1969. So here's where this leaves us. A mission that lasted 8 days in 1969 produced 22 kilograms of material and 21 days of seismic data that scientists are still actively interpreting in 2026, 57 years later. A magnetic mystery that outlived most of the engineers who built the instruments that first detected it. Vaults of untouched lunar material sitting in Houston right now, waiting for tools we haven't built yet. And a new generation of astronauts, currently training, currently testing hardware, aiming for a lunar surface landing, that keeps sliding a little further down the calendar even as the rockets get built and the crews get named. Nobody involved in any of this thinks the story is finished. Not the scientists still running Apollo samples through neutron beams. Not the mission planners still adjusting Artemis timelines month to month. Not the researchers who just spent 2026 solving a 57-year-old magnetic paradox, only to immediately start asking what else those rocks might be hiding. Which leaves one real, unresolved question hanging over all of it. The next time someone opens one of those sealed Apollo 11 sample containers, using an instrument that doesn't exist yet, built by someone who probably hasn't finished their physics degree yet, what will it tell us that nobody in 1969 or in 2026 ever saw coming? We don't know yet. Nobody does. That's kind of the point. 57 years ago, nobody knew the magnetism question. Would take until 2026 to even partially answer. Nobody knew a scoop of dust called Sample 184 would still be generating new papers when the astronauts who helped collect its cousins were long retired. The one honest prediction anyone can make about the sealed vault in Houston is that it will surprise somebody, eventually. It already has, more than once. If stories like this, the ones hiding in the footnotes of history everyone thinks they already know, are your kind of thing, stick around, subscribe, and we'll keep digging through the parts of the record nobody else bothers to read.